So the network covalent atomic solids, here we have atoms covalently bonded to each other. Elemental carbon exists in several different forms. These are called allotropes. Graphite is one. If you're writing with a pencil, you're smearing graphite on the paper. Graphite has carbon atoms that are covalently bonded to each other in two-dimensional sheets, and then those sheets are attached to each other by dispersion forces. That makes it slippery and makes it soft, and so as you move the pencil across the paper, you leave a trail of graphite behind as the layers slide away from each other. It's also conductive because there's an extended pi bonding network, and that gets back to molecular orbital theory. There's a pi bonding network above and below that the electrons can move around in. Graphite has a density of 2.2 grams per cubic centimeter. Diamond has a density of 3.5. You can take graphite, and under extreme pressure, you can cause the atoms to rearrange and form a crystal diamond. Here we have the atoms are covalently bonded in 3 dimensions. They're not layered sheets. It's all one covalently bonded molecule, essentially. The diamond unit cell is similar to this zinc blend unit cell that we looked at earlier. The difference here is that the atoms in the tetrahedral holes are also carbon. And so here we have carbon, and it's got tetrahedral single bonds to other carbon atoms. Those bonds are very strong. Diamonds have a very high melting point. It's also an excellent heat conductor, which makes it useful as an abrasive. You can get a diamond circular saw blade, and so the diamond is useful because it's very hard, but it also isn't going to melt. And when you have a blade going through material at high speeds, you get a lot of friction, and it gets very, very hot. So another kind of form of carbon was found in the 1980s, and these are called Buckminsterfullerenes. So here we have essentially a ball formed of 60 carbon atoms covalently bonded together. It's a lot like a geodesic dome. These can come in different sizes, from as small as 36 up to over 100 carbon atoms, and they're called buckyballs for short. Really cool things. This is the graphene that was mentioned in the very, very beginning. A graphene sheet is a single layer of carbon atoms covalently bonded together. So a single layer of graphite, essentially. It's very, very strong, very lightweight, and very thin. It's one atom thick, right? You can make this into ribbons or into tubes. This is a single-walled nanotube. This is a multi-walled nanotube where you've got multiple tubes inside of each other. Yeah? Carbon fiber is made out of carbon. That's this, yeah. Yep. So these are what make up carbon fibers. So carbon fibers are super useful. They are 100 times stronger than steel, but only 1/16 as dense. And so, you know, if you want something that's lightweight and strong, like a golf club or a bicycle frame, that's going to work out pretty well. Yeah.
Why is it so much more expensive to have carbon fiber than steel?
Because carbon fibers are more expensive to produce than steel. Yeah. Carbon fibers conduct electricity, and so you can use bundles of nanotubes to form tiny wires. So you can form wires using these nanotubes that are going to be much smaller than would be practical, say, from copper or another metal. Lots of cool applications for that. Another type of network covalent atomic solid are silicates. And these can be a little bit confusing because when we look at this formula SiO2, we think, oh, silicon dioxide, a molecule, one silicon atom, two oxygen atoms, molecular solid. But it's a network covalent solid with a ratio of one silicon to two oxygens because these are all covalently bonded in an extensive three-dimensional network. So the structure is such that the silicon is in a tetrahedral hole between the oxygens. Silicates make up 90% of the Earth's surface. They're common in ceramics, cement, glass. Quartz is one form of silica. Sand is largely silica.